I will do my second video on finding the general term and sum. You know what? While I was editing the last video, I discovered that I made my solution a lot more complicated. There is a much simpler way to get the general term of a geometric sequence, and somehow I missed it. My solutions were correct, but they were longer. And so I will devote another video for this topic, finding the general term and sum of a geometric series. But there is a shorter way and less complicated way to find the general term. We are still in example 2.21, find the general term and sum of a geometric series. This is our series. What is the general term? The general term is the formula that will tell us the terms of the series or the terms of your geometric sequence. And there is an easier way to write the general term. We look for the common ratio. In the last video, we did look for the common ratio, but we were coming from a different direction. Today, we will come from the definition of a geometric sequence. Every pair of consecutive terms of your sequence has a common ratio. And so, to get that common ratio, what we do is we just pick any pair of consecutive terms and we get the ratio of the later term to the earlier term. So let us pick the first two terms. Negative square root of 3 over 3 over 1 is this. This is our common ratio. We now go to the part on writing the general term. This is our general term, but then again, you must double check it. The way to double check it is to pick values for n and check if the resulting value of your term matches the first few terms of your series. Okay, so when n is 1, this is 0. Any real number raised to 0 is 1. So we got the first term right. When n is 2, 2 minus 1 is 1. This raised to 1 is this. We got the second term right. How about the third term? When n is 3, so 3 minus 1 is 2. We will square this. And when we square this, this is positive. What's the square of the square root of 3? It's 3. What's the square of 3? It's 9. There is a common factor. 3 is a common factor, so it becomes 1/3. So we got it correct for the third term. So this is our general term. Let us write the geometric series. The geometric sequence is different from the geometric series. The sequence are each of these individual terms. 1, negative square root of 3 over 3. 1/3. Negative square root of 3 over 9. Those are the first 4 terms that compose your geometric sequence. But when you added them, and when you produce your sequence of partial sums, that is the geometric series. What is the sum of this geometric series? Well, not all geometric series converge to a sum, but this one does. Why? It has to do with the common ratio. The common ratio is, or at least the square root of 3 over 3 is equal to 0.58. And so the absolute value of that is less than 1. And we had a theorem for this. When the absolute value of your common ratio is less than 1, the sequence of partial sums or the geometric series, they are the same things. They converge to a finite sum. What is that sum? Well, this is the sum. Where did this sum come from? It came from this. So be careful with your signs. Look at the denominator. 1 minus negative square root of 3 over 3. That becomes 3 plus square root of 3. Okay, so this is about simplifying a complex fraction. In the last video, I did not go as far as simplifying a rational expression with a radical number. But in this example, let us rationalize the denominator. To rationalize the denominator means to find an equivalent fraction so that you don't have an irrational number in the denominator, or in particular, a radical number. So this one, square root of 3 is an irrational number. So we multiply it by this. You call this the conjugate. This one is the conjugate of this expression. Okay, I will not go through that. And doing the multiplication, it will give you this expression. I will leave it to you to verify this multiplication. Find the general term and then the sum of this geometric series. What is the general term? Well, we need first to find the common ratio. Again, how do you get the common ratio? Each of these terms is a term of your geometric sequence. So what you do to find the common ratio, you pick any pair of consecutive terms. Well, let's make our life simpler. Let's just pick this. Get the ratio of the later term to the earlier term. Square root of 2 over negative 2. This is your common ratio. Let us write down the general term. Again, you must be careful. Just to be sure that you write the subscripts correctly, the initial terms and the common ratios correctly, well, double check. Will this duplicate this, at least the first 3 terms of this series? Well, when n is 1, this is 1. Any real number raised to, okay, look at this, 1 minus 1 is 0. Any real number, any non-zero real number raised to 0 is 1. So 1 times this will give you that. So we are correct in the first term. How about when n is 2? So 2 minus 1, that's 1. This raised to 1 is itself, we multiply it to this. Now look at what happens. 2 is cancelled. Square root of 2 times square root of 2 is 2. And then because the power is 1, we keep the negative sign. Negative 2. You can try it with the third term and the fourth term. But you know what? If this is an exam, if this is an item in an exam, I think checking for the first 2 terms would be enough. Let us now write the geometric series. So when you write the geometric series, it is a summation. It is a sequence of partial sum. And we are using the summation notation to write the series. This is it. You can choose any index, I, J, K, N. Does the sum exists? It depends. It depends on the common ratio. But for this particular series, the geometric series converges to a sum, to a finite sum. How did we know that? Because of the common ratio. Square root of 2 over 2 is 0.71. So that means the absolute value of our common ratio is less than 1. The geometric series or the sequence of partial sums is converging to a finite sum. What is that finite sum? This is the finite sum. Where did this come from? It came from this. Let us simplify this. This is a complex fraction, so let us simplify. This is like practicing. We must rationalize the denominator. Let us multiply it by the conjugate. You call that the conjugate. If this is 2 plus square root of 2, its conjugate is 2 minus square root of 2. But we multiply it by this expression, okay? Because this is equal to 1. You know what? When I was in college, I cannot understand. Why do you multiply this by this one? If this is the conjugate of that, why do you have to copy this in the numerator? No, I'm not kidding. I didn't know that. I will leave it to you to figure out why. Okay, so this is equal to 1, all right? This is equal to 1. So when you multiply this to this, you are not changing the expression. Whereas if you will not copy this in the numerator, you are changing the sum. So simplifying this will give you